Hi everyone. Just sorting out some technical difficulties, but my name is Linda and I'm excited to introduce Michelle Wei, who is a Regeneron STS third place winner and a qualifier for the International Science and Engineering Fair this year. So Michelle first discovered her interest in math when she was young, participating in many math competitions throughout middle school and high school, such as AMC, AME, and USEMO. She finds beauty in the interconnectedness of the world of math. Over the last 2 summers, Michelle directed a summer program to introduce advanced math to middle school and high school girls across the world. Wanting to explore mathematics at a deeper level, Michelle joined the Primes USA Math Research Program, where she conducted research in graph theory as well as mathematical optimization. A fun fact about Michelle is that she also loves playing volleyball and piano. Today, Michelle will be presenting on her research titled Solving Second-Order Cone Programs in Matrix Multiplication Time. Let's give her a warm welcome.
Hi, I'm Michelle, and today I'm going to be talking about my research on solving second-order cone programs in matrix multiplication time. Okay, so first I'll give some background on mathematical optimization and second-order cone programming, and then to give everyone an idea of how to solve mathematical optimization problems, I'll talk a little bit about interior point methods, and finally I'll be talking about my work on developing an efficient new second-order cone programming algorithm. Okay, so first of all, what is mathematical optimization? A lot of fields have problems where we need to make some decision, and we want to do so to either minimize costs or maximize profit while adhering to a specific set of constraints. So how do we find the optimal decision to make? Well, we can represent this problem mathematically by defining a couple of things. So first, we can define a vector x such that each component of x corresponds to a parameter that we can control in our decision making. We can also define f of x to be a function on x representing cost, and we can define c to be the set of all valid x that satisfy the constraints that we want. And so our mathematical optimization problem would be to find the minimum of f of x under the constraint that x is in C. So this is a general setup for a mathematical optimization problem, but also we wish to apply constraints on f and c that will allow us to find efficient algorithms to solve that specific class of problems. So one of these constraints is convexity. So often we're interested in convex optimization, so optimization problems where f and c are convex, because these problems are easier to solve and many of the practical applications of optimization can be represented with the convex program. Within convex optimization, there are many smaller classes of problems, including semi-definite programming, second-order cone programming, quadratic, and linear programming. So in my work, I was focusing on second-order cone programming. So second-order cone programming is useful because it provides a general framework for solving a lot of different optimization problems in a wide range of fields. For example, finance, machine learning, or energy. So in finance, for example, SOCPs can be used for portfolio optimization, which is when we want to find financial portfolios that minimize risk while reaching a threshold return value. Another example is support vector machines, which are a type of machine learning algorithm that aim to find the optimal separation between data classes. SOCPs can also be used to find an optimal way to distribute power within a power system while concerning constraints such as maximum generation capacities in a power plant or maximum voltage levels across the line. So a lot of different problems across fields can be represented with second-order cone programs. Okay, so now before I go into the definition of a second-order cone program, let's first talk about second-order cones. So a second-order cone, LK, is defined as the set of all ordered pairs x0, x tilde, such that x tilde is a k-dimensional vector, and we want the norm of x tilde to be less than or equal to x0. So for example, when we think of the word cone, we usually think of something like an ice cream cone, as you can see in this figure here. So we can see that the definition of the second order cone L2 actually matches up with the equation for this cone, which is square root x squared plus y squared is less than or equal to c. And so it's a little bit harder to picture this in higher dimensions, but this definition here allows us to generalize this constraint to higher dimensions. Okay, so now for the definition of a second order cone program, the objective function, which is the cost function that we want to minimize, is linear. So we can represent it as C transpose X. So here C and X are both vectors. So C transpose X would be the dot product of C and X. And the constraint function would be the intersection of an affine set AX equals B and the Cartesian product L of second order cones. So what this means is we have our vector X, we would break it up into different blocks. And we want each of these blocks to lie inside the corresponding second order cone constraint. So for example, here would be an example where we have 3 blocks, x1, x2, and x3, and we want each of these, we want 3 things to be satisfied. We want x1 to be inside L1, we want x2 to be in L2, and we want x3 to be in L3. And we also want AX equals B. So that's a little bit of a complicated definition, but that's the definition of a second order cone. Okay, so here's a more formal version of the definition. Okay, so now how do we actually solve second order cone programs, or even a convex program more in general? So one of the major breakthroughs in convex optimization was Harker's result in 1984, where he developed interior plot methods. So initially he did so for linear programming only. And then in 1994, Nesterov and Namorowski were able to extend this result to general convex programming, and they were able to produce an algorithm for second order programming that runs in O of n to the omega plus 0.5 time. So that's the time it takes, so n to the omega is the time it takes to multiply 2 n by n matrices together. And so for reference, the value of omega is about 2.37 currently. And so recently there have been a lot of advancements in some of the more narrow types of convex optimization, and these were all able to achieve O of n to the omega time algorithms, which is the same as matrix multiplication time. So the time it takes to multiply 2 n by n matrices. But the best result for second order programming is still this 1994 result from Nesterov and Namorowski, where we have this extra square root r term, or square root n term in the time complexity as well. So in my work, I was investigating how to develop an algorithm for second order cone programming that would match the time complexity for linear and quadratic programming, but solves a broader range of problems. Okay, so as a summary of my approach, I developed a second order cone programming algorithm that runs in matrix multiplication time. And to do so, I applied approximation techniques to reduce the runtime of each iteration. And I also developed a novel approach to decompose large constraints into small ones. And combining these two things, I mathematically proved that the new algorithm converges in matrix multiplication time. Okay, so now let's talk about some of the algorithms in convex optimization. So given a second order program of this form here, we can define another SSCP, which we call the dual, which would be something of the form here. And so we would call the original SSCP the primal second order cone program, and this new one is the dual. And so we can kind of think of it as another second order cone program that provides a lower bound for the minimum value of the original. And this is really useful because there's a theorem known as complementary slackness, which says that any feasible x and x are optimal if and only if x transpose x is equal to 0. And this is useful because what this allows us to do is we can start with some feasible solution pair xs, and then repeatedly apply some update to x and s that would take us from this initial point over here, as you can see in this figure. We would update it repeatedly until we reach the optimal solution value. And we would know that we've reached the optimal value when x transpose s is sufficiently small. So when it's below some error value that we tolerate. So at every step of the algorithm, we would compute delta x and delta s, which are the updates on x and s. And then we would update x and s to the new point. So that's a general algorithm that we can use to solve this problem. And in order to do so, at each step we would solve a linear system in order to compute delta x and delta x. However, it's really computationally expensive to solve this system exactly at each iteration because this requires matrix inversion, which takes O of n to the omega time. And so instead what we can do is to reduce this cost, we can use some approximation x bar and s bar to solve the system instead of the exact values of x and s. So what this allows us to do is to take the solution to the system at some previous iteration, apply a small update on it, and find the new solution much more efficiently. And to ensure that we stay sufficiently close to the central path, we would have to develop an update procedure on x bar and s bar to update selective blocks of them strategically at each iteration to ensure that it remains close enough to the central path. So as you can see in this diagram, instead of taking the exact central path, which would be this blue path over here, we can instead take some path that stays within some central neighborhood of this blue path, but is much more efficient to compute. Okay, so now even without recomputing the solution from scratch at each iteration, it's still very expensive to update a high-dimensional block when the dimension ni is large, because this requires inverting ni by ni matrix. So instead what we can do is we can find a way to transform high-dimensional cones into the intersection of smaller cones in affine space. So for example, if we have a second-order cone L2k, then we can split it up into 3 smaller cones, 2 of size k and then one of size 2. So that would be L2. And then we can also add 2 more linear constraints. And so what this does is we can take our original second-order cone program and convert it to a new second-order cone program where we're able to quickly reconstruct the solution to the original from the new one, but it's much more efficient to solve because it has lower dimensional constraints and we don't need to invert these large matrices. So this allows us to overcome the variability that we have in the block sizes within a second order. Okay, so putting together approximation techniques with code splitting, I was able to develop a new algorithm for second order cone programming that runs in O of n to the omega time. So here's kind of a complicated expression, but for the current values of omega and alpha, which represent different types of matrix multiplication, this essentially reduces to O of n to the omega time. So this is able to match the time complexity of linear and quadratic programming, but is able to solve a wider range of problems. And with this new algorithm, we're able to speed up decision-making processes in a very wide range of fields. I'd like to thank my mentor, Kwang Hao for all his guidance and encouragement throughout this project. And I would like to thank Dr. Ettinger, Dr. Girovich, Dr. Kovanova, and all the MIT Primes organizers for making this math research opportunity possible. And thank you all for listening.
So now we're going to open it up to Q&A. Please go to the Connects Me app and click on this section and then click View Feed and you should be able to ask questions. For now, I have a question. Michelle, what was your thought process when coming up or choosing the approximation techniques and splitting up the cones? Like, how did you think of it?
Yeah, so I think a lot of the ideas for approximation techniques I got from reading a lot of papers where I saw that other researchers were doing similar things, especially for linear programming. And so the reason for approximation techniques is because we want to find a way to overcome this time barrier that we have, which is when we have to invert this very large matrix at every step of the algorithm. So by using an approximation technique, we're able to utilize the solution from some previous iteration of the algorithm in order to find the solution for the current iteration. So this allows us to do that much more efficiently instead of having to invert this matrix from scratch at each iteration. So that's kind of the motivation for doing this approximation technique. And for the code splitting as well, this is because it's very highly computationally expensive to invert matrices corresponding to large blocks in the second order cone problem. So by splitting the large second order cones into smaller ones, we're able to control this control of the sizes of the second order quantum constraints in the SOCP, and this allows us to overcome another point where we would have to invert large matrices. So these two things combined, generally the thought process behind them was to be able to overcome this problem where we have, which is having to invert large matrices in the algorithm, which is highly computationally expensive.
Okay, cool. And then a question someone else had was, how did you decide to pick this problem to work on?
Yeah, so I decided to pick this problem to work on because I really like math and computer science, and so I ended up joining the Prime USA Math Research Program, and so when my mentor asked me what I wanted to do, I knew I wanted to do something that combines those two fields. And so for this specific problem, my mentor gave me a lot of papers on convex optimization to read about, and I think I just ended up being very interested in second order programming because it just has so many applications to it, and I wanted to see if some of the recent advances in linear and quadratic programming could be kind of modified to also apply to second order programming.
Cool. And another question is, do you plan on doing any future work on this? What are some future improvements you can do on the research?
Yeah, so one future improvement would be, so I was able to implement this algorithm using code, but I think one future improvement would to apply it more to specific applications. So right now this is an algorithm for general second order code programming, but in order for it to be more useful for applications, we can take advantage of the specific features that we would have for the different applications in order to tailor this algorithm to those applications. So that would be one future improvement to make, to just extend this algorithm to be able to make further optimizations that cater to specific applications.
Cool. And last question, are there any theoretical limitations or practical considerations that could affect the scalability or applicability of this algorithm?
Yeah, I think one of the things is also, in order to apply this, I think there still has to be optimizations to be made in the actual implementation of the algorithm. I think, for example, like I just mentioned, there has to be, in order for it to be more useful for actual applications, I think it would be useful to have different optimizations within the implementation to tailor it specifically to those different fields.
Okay, if no one else has any questions, I think we can end it off there. Thank you, Michelle.